and welcome to our podcast. And this week, Ed Supply podcast. And I want to talk real briefly. This one's not going to be a long podcast, but I've had a lot of people ask about this, and I'm going to kind of put it out there as quick as I can. Those that are listening by YouTube, there'll be some slides on this. So you maybe want to look at that, or if you're just driving and listening, that's fine too. You can always go back and look at it wherever you're listening to this at, whether it be on Spreaker or on iHeartRadio or Spotify, uh, iCast, uh, YouTube, or on our website, tsaedsupply.com. You can find these podcasts on there. But basically, we're dealing with ICP equipment. Now, what we're going to talk about today will actually involve or the same brands, whether it be a Goodman, whether it be a Train, American Standard, Ream, Rude, whatever you're going to put in. These kind of principles are the same, and this is what ICP calls a basis for a good install. Now, understanding what a good install is, a good install means that the equipment has been installed exactly as it was engineered to be installed. So, ICP, Train, different ones. You think about these companies that are billion-dollar a year industry companies design equipment and put out an install manual that says this is how you are to install this piece of equipment. Now, this is my 29th year going into the HVAC industry, and that doesn't mean anything. I mean, the equipment changed last year. So if I'm still installing equipment the same way I did 10 years ago or 15 years ago, I'm having issues. I'm definitely going to have problems. Couple reasons why. The motors are different. They went from a PSE motor to a OEM motor. You got to understand the difference with those motors. They go from different kind of windings and magnetic motors and et cetera. And that's a whole different podcast. But understanding the motors are different and the compressors are different. We go from a reciprocating compressor to a scroll compressor. Different beast, different animal, different temperatures, different pressures, different freon. A lot of things have changed, so we're going to install things different. Now, when the X13 motor came out, everybody cussed it. I was a service tech then, and I remember just hating that motor with a passion. The problem is the motor should have had a memo with it that said this motor is airflow sensitive. Make sure you set the airflow, the capacity or the static pressure, if you will. We're going to talk a little bit about that today. Now, but I want to kind of give you, maybe you're a service tech that hasn't really been through a training, but you've been doing it a long time and you've had to go into your own business or start your own company, or you're doing things for a friend, or you're installing this on the side, or maybe it's your side hustle, or maybe you're a licensed contractor and have never went to any kind of schooling or training for the equipment you're installing. Now, this will help you for that, and that's what this is meant to do. Is meant to help you. Some of the stuff you're going to see here, everybody does it different, and everybody's got their opinion on how they do things and how they've been doing it for years. And I can't speak on that. All I can speak for is this is what ICP uh, sets theirs up. Now, what we're going to go over, some of the math, isn't per ICP. This is a math equation that I've came into about 28 years ago from an individual who was a service tech, who was very professional, showed me then, it was R22 days back then, showed me this formula. And I found out that a lot of people still use this same formula if you don't have access to a manual J or a heat load. Like there's a lot of our installers that don't have a manual J or a heat load on the unit they're going to install. So here's what we're going to kind of get into. So the first thing we're going to do is we're going to talk about a random house. Let's just say you get a phone call They find your name and number and whatever, and you go visit this house, and you look the house over, and you're going to size the house, and they need a new piece of equipment, and you go in and go, well, there's a 2.5 ton, 2 ton, uh, let's say a 2 ton system was there, and so you think, well, I'm just going to take this 2 ton out, and I'm going to price them a two ton unit. And then you always hear the thing, well, I like 2 tons so good, let's go with a three. Or maybe I want to go to a three. Or maybe you're just kind of looking at, maybe you got an extremely good deal on a unit, and you need to move that unit, and you want to offload it onto this customer, or you give this customer a break, or you give them a deal, or maybe that customer is on hard times, and maybe they need some assistance or need you to work with them, or whatever the case may be. um, we're going to talk a little about how you can still do that, but also make sure you're putting the equipment in right, because end of the day, we want to stop callbacks. That's why we're doing this podcast. That's why we're talking about this, because companies are going out of business because of callbacks. The reason they're going out of business for callbacks is they don't really understand the equipment. Now, maybe granted, they know how to sweat copper, or maybe they know how to charge a system, or maybe they know how to read a gauge and understand what pressures are, and saturations and subcooling and superheat. But maybe they don't understand when you get to a job and you put your gauges on it and the subcooling's off, and the first thing you think of, it's low a charge, and you put charge in it, and you really don't see a difference. A homeowner calls you back in 2 or 3 weeks and says, hey, this thing's still not acting right, still running all the time, or whatever the case may be. Then you realize, uh-oh, we something else going on. So you have to go back to the job. Or maybe you install this equipment and the homeowner just says, hey, my light bill went up. This thing runs nonstop. I've got those phone calls. And from people that have installed our equipment, brand new houses, brand new equipment, that says, hey man, our unit has not shut off. It's nonstop running, and it's junk, or it's not working right, or it's not doing the job. And my job is to go out to the job site and actually figure out why it's not working right, and make sure it is a bad install, or is it a bad piece of equipment. And so that's what I get to do, and enjoy part of my job on that. But I've also learned a lot through this uh, job to understand what ICP does, and we're going to talk about that. So let's say we take this house, and we're going to look at this house. If you're looking on the screen, if you have time to look at it, you'll actually see this. And let's say this is a 3 bedroom house. It's just a standard 30 foot by 48 foot house, open concept when you walk in. And this, say this house had a 2 ton unit on it. Because let's kind of look at it. So if I'm looking at this and I look at the size of it, so let's say it's a 30 by 48. That's 1,440 uh, square feet. And let's say some people go in and they divide it by 600, and you wind up with a 2.4. So somebody had a real good deal on a 2 ton unit. They put a 2 ton unit, and it's been in there for years. And the homeowner says, hey, this thing's been in here forever. We just want something more efficient, or they're just, the unit, my light bill seems to be higher, whatever the case may be. So I'm going to tell you what ICP uses, and they would, 30 times 48 equals 1,440 square feet. So they're going to divide it by 500. And that's what ICP says is 500 square feet per ton. So you look at this and you go, okay, not 600. And I've heard 100 people say it different. When I was in the business, when I first started out with Allied Mechanical back in 96, I'm sorry, 94, we looked at this, and it was back then, it was 400 CFM per ton, and it was 400 square feet if it was commercial with concrete floor, lay and ceiling, or if you look at 500 CFM if it's a normal house with insulation. And then some people were even going 600 and 750 and all kinds of numbers. but ICP generally wants 500. So if we look at this house and we see it is 30 by 48, divide it by 500, and that comes out to be 2.88. Now, some people would look at that and say, okay, well, I could go with a 2.5, which is a little under, or I can go with a 3-ton. So in this situation, we're going to take a look at the numbers between a 2.5 and then a 3-ton. But let's say in this situation, um, you look at, okay, well, I've got a house that maybe the living room and the kitchen, this open concept, has 10-foot ceilings, or maybe they're kind of gabled a little bit, architectural type ceilings. So we have a little bit more heat load because the ceiling's a little higher. So we're kind of deciding what to do. So let's just say, first thing we need to do is get our square footage, and we're going to get our square footage from each room. So if you look on the map we have here, we have 3 bedrooms. There's a 15 by 14, another 15 by 14, a 12 by 14, a bathroom connected to the master bedroom that is a 12 by 8, the master bathroom, a 12 by 10, a laundry area, a kitchen and dining room at 18 by 16, and a living room, 12 by 20. Now you'll also see some of these houses, we got a hallway. We didn't add that up, but you'll see how this plays in to the road going forward. So first thing we want to do is we want to get our square footage. So if you look at the next screen, this bedroom, 15 by 14, 210 square feet. Got another bedroom, 210 square feet. The half bath is 96 square feet. The main bathroom is 120 square feet. The third bedroom is 168 square feet. The living room is 300 square feet. And the kitchen dining room area is 240 square feet. Now, if you're looking at the screen, and you'll notice this area right here, we don't have any sizing for it at all, because this is where we're going to stick our return. So we could easily mount our return somewhere in this area here, and all the air is going to come through here and naturally help that airflow out. So that's kind of why we're setting this up. And this is strictly to give you an idea of what you need to do, no matter what house you're going into. Or maybe this is an upstairs and you're just doing a 2-ton upstairs. Wherever the unit you're fixing to set is going to be conditioning the air, that's where you need to have this square footage. So we understand these are our numbers to our square feet. So the next thing we're going to do is we're going to take our 2.8, and we're going to look at that, and we're going to go on up. Since we have a higher ceiling here, we're going to go to a 3-ton. So a 3-ton is 1200 CFM. So it's 400 CFM per ton. So 4 times 3, 1200 CFM. So we're going to take our 1200 CFM and we're going to divide it by the 1440 that is our square feet. And you get a 0.83. Now, we're going to share something with you on this number. This 0.83 is an important number. Now, I have seen websites where I think it's Slide Rule or Slide Cool Rule. He goes with a 0.80. You can take it. Let's say you're going with the numbers when you added them up, instead of a 2.88 was, let's say, a 2.56, and your number was more like a 0.76. So this was the math formula that I was given back 28 years ago, 27 years ago. And he said, this is how you actually do it. You take your square footage and you multiply by this, and you get this 0.72 or 73 number. And you take that number and you multiply it by the square footage of each room. And then that's how many CFMs that room needs to heat and cool. This is based off of 8-foot ceilings, normal 3-foot by 3-foot bedroom window. Now, of course, if you have a wall full of glass or a storefront or higher ceilings, you really need to get a manual J. So finding out what is my heat load, you need to know what your heat load is for a couple of reasons. When you're setting a furnace, let's say this one is going to be a split system, and we're going to use one of our 3-ton air handlers and a 3-ton heat pump condenser on the outside just for this particular podcast. And we can go over different ways of doing it in another podcast. But this one, we're going to put in a split system, a 3-ton split system, and we're going to use our equipment would be a N4H5S36, and indoor would be a FJMA4X36. So this is ICP's 3-ton Temp Star um, split system that we're going to install. Now, in doing this, I want to show you the numbers though. I want to go back just a second, and without trying to be too confusing. And let's say you're that guy that says, well, I can get a better deal on a 2.5-ton system. I just want you to see what these numbers are going to look like. If I was to go with a 2.5-ton, well, that's 1,000 CFMs multiplied by the 1440, and you would get a 0.69. And this would be your numbers if you looked at it. And all the ones in the green, that represents the CFMs required for a 2.5-ton system. So if I took 210 square feet and multiplied that by 0.69, I get 144.9. And that's the one we're looking at right here, the 144.9 CFM to heat and cool that room. Now, same way with the bathroom. If I was using a 2.5-ton, I would do my 0.69, and I would come up to 66 CFMs for the half bath, 82 CFMs for the main bathroom. Bedroom number 3 would be 115, 207 in the living room. And then what I would do is I would add all these numbers up, and that's how much I would set my capacity for. Now, that probably just threw a bunch of people a loop when I said add those numbers up and set my capacity at that. You're thinking, what are you talking about? Well, that's why we're doing this podcast, because so many installers would probably stop right there. And I've seen installers that would say, well, this room looks like a 7-inch. Let's put a 7-inch. Well, if I put a 7-inch right here, and let's say I'm hard piping it, well, that 7-inch is going to carry 150 CFM hard pipe, but it's not going to carry 150 CFM on flex. Now, your flex measurement on that would be a little different. So if we looked at what does flex carry, you're looking at roughly the flex. If you go with a 0.05 friction, which is what ASHRAE uses, then that 7-inch flex is only going to carry 110 CFMs. So if you're doing a 7-inch flex here, you're going to need to go up to at least 8-inch, and 8-inch would carry 160. So you would have to go with an 8-inch flex, and then take your takeoff. You would want to take off with a damper, and you'd actually dial that damper back a little bit to get this 144.9 in, and we'll talk about that in another podcast as well. But that's kind of where I want to look at is you see these numbers based off this, and you would add it up and you would set your capacity. But we decided we were going to go with a 3-ton. So if you look at the numbers in orange, that is the CFMs that you would use for a 3-ton. Now see how things have changed. So now you look at, I've got options now in the bedrooms, in the living room, and in the kitchen area, because now our numbers changed because we went with a 3-ton. So we had to take 1,200 and divide that into 1440, which is our square footage of our house, and our number was 0.83. And like I said, Slide Cool Rule uses a 0.80 across the board, and that works as long as everything else works out. So this is just an example to give you an idea of what you need to do. But I wanted you to just see that just changing from a 2.5-ton to a 3-ton unit, how much CFM that room is now going to take under. Now you look at, there's quite a bit of difference. This one here in the kitchen, you're talking about 30 CFMs. This one in the living room, you're talking about almost 38 CFMs. So you start adding all these up and you start seeing, hey, I'm having the opportunity of having a higher, if I have a more of a heat load, let's say we got higher ceilings in this area, or let's say we got French doors here or sliding glass doors going out to a back porch, and this is eastern, the sun sets in the west, so I have evening sun coming in on the back side of this kitchen beating down, so I'm gonna have a more of a heat load in the evening time. So those things you got to keep in consideration. But let's say we went with, for the sake of this podcast, we went strictly with a 3 ton unit. So let's get rid of the ton and 2.5 ton numbers and let's stick with our 3 ton numbers. And so now I'm looking at that bedroom needs 174. Well, we just said 8 inch carries 160. So now my 8 inch is going to be too small because I need 174. So here's where your options come in. I can take 2 7 inches and put them here and turn one down, or I can put a 7 and a 6 inch. All right, same way here, a 7 and a 6. That would give me quite a bit more airflow, and then I would make sure I would size it down and damper down which one I needed. Same thing here. I can put a 6 inch in this half bath. I do believe, but a 6 inch, according to ASHRAE, with a 0.50 is going to carry right at 75. So a 6 inch is going to be too small. So I'm going to have to put in a 7 inch and then damper it down. And then on this one, I would have to use, on that bedroom, I could use a 7 inch and damper that one down as well. Here we have 139. So this one's going to have to be an 8 inch and dampered back. This one I'm having two options. I could do a 7 and a 6. And then here in my living room, of course, I would want multiple options. So we may do one here, may do one here, and in the kitchen, depending on how the layout is. That's something you can actually figure up yourself. But you look at, here's the number I wanted you to look at here where the arrows are. This all added up is going to give us 1115.4 CFMs. So just, this is, like I said, strictly for demonstration purposes only. This isn't a real house. This is just for demonstration to let you understand that if I take this house and I take each one of my rooms and I get my square footage from each room, and then I take my 3 ton, 3 times 4 is 1200. So I take 1200 and divide that into the 1440 square feet area. I get a 0.83. And so I'm going to go with a 0.83 number to make sure I get the right amount of CFMs from my unit for these areas. And like I said, if you were going with a, like if you went with the slide, the slide cool rule, his is 0.80, and the 0.80. So let's see what that would be times 0.80 equals. That would be 168 here instead of a 174. So you can see how these numbers are changing depending on what you're using and how you're going to use it. So that's one thing that we really need to understand, because you're going to see how this is going to work going forward. So let's just say that here's how we're going to do. We're going to take the 3 ton, 1200 divided by 1440, which is our square footage, get our 0.83. Then we take the square footage of each room, multiply that by 0.83. That tells me how many CFMs each room needs. And I have a total of 1115.4. That's where I have a minimum I have to set my capacity at. And you're asking me, what do you mean when you say set the capacity? Well, if you'll open up your manual and turn to right, usually around between page 11 and page 14, you see this table number 3 right here on this particular piece of equipment, ICP. And you're going to see external static pressure. You're going to see the ton size. You're going to see the blower speed. And you're going to see these numbers here. These numbers represent your static pressure. Now, let me share with you that our older model, as of 2 years ago, we had a FEM4X. That FEM4X only went to 0.6. Anything over here was damaging the equipment, which means that in a year to 2 to 3 to 4 years, your compressor would go out because of excess pressure pushing back into the compressor, or you would pop a coil, or your X13 blower motor would go out. And so now you kind of understand why there was so many X13 motors going bad in the beginning, because a lot of homes were in this high static area because a return duct was too small or the return grill was too small. Those things have to be sized right, or you're going to have equipment that's up here in this danger area. Now, when we looked at this number a while ago, let's go back to this, the previous screen. If I can't get it to cooperate, so we'll stay where we're at. 1115 was the number we needed. All right, so 1115. So if we look on our chart now, when you get your furnace, it's going to come from ICP because it's tested from the factory. Speed tap number 2. Now, let's just say this: I get a 3-ton air handler, and when I put it in, does it mean it's blowing 1200 CFM? Most people would say, well, yeah, that's why we put it in. Okay. The speed tap's on speed tap number 2. Where on that chart do you see 1200 at speed tap number 2? You don't, because it's not blowing 1200. So understanding that, now what do? Well, most people would say, well, I'll move it up to speed tap 3 because I see there's some 1200s up there. And that's correct. You could do that, providing your static pressure doesn't move. Now, how do you check this? Well, there's a podcast we've done that is solely on static pressure. So you would take your dual manometer, and I use a Fieldpiece dual manometer. I have the Bluetooth ones, and I also have the SDMN6 packet that has the duct probes. Put them in, and I'll read what that static pressure is. Now, what I want to point out real quick is when you do that, anything over 0.3, now get in mind, ICP does not want any of your equipment higher than 0.5, period. Now, if you're in cooling mode, the most you can go is 0.5. Now, keep in mind, this unit will operate into the 1.0. But if I look at 0.5, which is where they want it, and I'm at speed tap 2, then that means, let's say my static pressure was around 0.52 or 0.53, and let's say I'm at speed tap 2, I'm putting out 1,051 CFMs, not the 1,200 I think I'm doing. But let's say if I'm in a high static of this 1.0, that unit's only putting out 783 CFMs. Now, imagine you putting a 3-ton system in, and that unit's only putting out 783. You're not even putting out 2 tons of air. Now you can understand why a compressor would blow up, lock up, open windings, go off on a high head, making all kinds of rattling noise, because pressure has to go somewhere. Now, I'm gonna address this real quick, that a compressor, now a standard heat pump is single speed. Now you'll have 2 speeds or 2 stages, and you'll have inverter compressors. But the compressors in our normal heat pumps, 14 and 15 SEER, are 1 speed. So as soon as you put power on it, that motor turns 1 speed, and it's pumping 36,000 BTUs. Now, you have to look at it. Some compressors actually put out, say they're 32s or 31s, but with the coil size that they have, it will produce 36,000 BTUs. Now, what I have to do is also understand that in that air handler, that coil, the indoor evaporator coil, is certain size tall, certain size wide, and it's made with a certain amount of fins across it to allow, if I have 1,200 CFMs blowing across that size coil, it will produce 36,000 BTUs. Now, so that's what I want to look at, is I have to have that much airflow coming across that coil to produce 36,000 BTUs so my house gets taken care of. So I have to have 1200 CFM. This is going to tell me what I have. So let's say I set my static pressure and I test it, and I'm way up here in the 0.9 number, all right, and I'm on speed tap 2, I'm only putting out 846. Well, I have to have 1115. So you can see I'm about 300, roughly almost, CFM shy. Now, if you look back at the map, that's 2 bedrooms we're losing, or a living room size area we're losing. So we have to get our 1100. So here we look at these 2 areas in the yellow, which mean these are over 1115. So if my static pressure was 0.6, I could move my tap up to 3, and as long as I'm in that 0.6 static range at speed tap number 3, then I'm going to get 1168 CFMs. Now, the unit will still operate. My capacity will be right. I'm running a little higher static than the health on my unit. What that means is, just like your body runs a higher blood pressure than normal, your organs will wear down more or quicker than they normally would. Where if my blood pressure was super low, if I get too low, I die from low blood pressure. But if I get too high, I die because of too high blood pressure. So I want a healthy blood pressure range. Well, that's what this is. We want a healthy static pressure range for your unit. And ICP says no more than 0.5. We optimally want to operate right here between 0.3 and 0.4. This is our optimum range. This is where we really want to operate in this area. Now, and to do that, you take the return and you add it to the supply static pressure. So you have a probe in your return, a probe in the supply. Anything over 0.3 is considered restriction. So we need to open that end up and make it. Usually you're going to find the probe in the return. If you do it right, you'll see that your return is a lot higher resistance than the supply. Now, a lot of people will put the probe in the wrong spot. Like I said, I'm going to refer you to the podcast on static pressure. It'll show you where to put the probes at. This is where ICP recommends probe placement on our equipment, so to test it. So in this particular case, here's what we need to do. We are going to look at the return that we talked about. We're going to set our flex. Let's say we're going to use flex on this one. And we're going to set it, what ICE-Ray said it, at friction rate of 0.05. And we need 1115. So we're going to set it for 1200, which is 18-inch flex. If we pull our 18-inch flex tight, then we use hard 90s and pull our flex tight, we will carry 1200 CFMs, a little bit more than that, back to our unit. So keep in mind, our units are not making air. We're moving air from one end of the house to the next. So when we talk about setting capacity, this is what we're talking about. If you check your static pressure and you move this pin to tap 3, but you don't check static, you could easily be in these danger ranges that's going to cause a compressor to go out in 2 years to 3 years to 6 months to 6 weeks. I've seen compressors last 6 weeks and go out. Usually if you've got a bad compressor from the get-go, it's going to be DOA the minute you put power on it, or you're going to hear it coming apart on the very initial startup. If you've had it running for a week or two and then hear the noise, it's on your install, which means you've done something, whether it's airflow, whether it's line sets. We'll address that in other podcasts as well. But this one here is strictly our airflow capacity we're going to talk about. So in this situation, we could take this speed tap, move it to speed tap 3, and make sure if we're in a 0.5 or less, we're safe with ICP, and we're making 1207 CFMs. Then I can go back and dial some of those rooms down or add a little bit more if I have a flow hood or any device like that, and we'll talk about that in other podcasts as well. But that's the main thing I kind of wanted to talk about in this podcast.